In this video, we're going to be talking about inferences about the slope of the population regression line. So the properties of our sampling distribution of B's. Now, since beta is almost always unknown, it must be estimated from independently selected observations. So the slope B of the least squares line gives a point estimate for beta. When the four basic assumptions of the simple linear regression model are satisfied, the following statements are true. First, that the mean of B is beta. So that's that the mu sub B equals beta. Second, that the standard deviation of the statistic B is the standard deviation divided by the square root of the sample size sub xx. And third, that the statistic B has a normal distribution, a consequence of the model assumption that the random deviation E is normally distributed. Now, since sigma is usually unknown, the estimated standard deviation of the statistic B is actually S sub B equals S sub E divided by the square root of S sub XX. So what about our confidence interval for beta? Now, when the four basic assumptions of the simple linear regression model are satisfied, a confidence interval for beta, the slope of the population regression line, has the form B plus or minus our t critical value times the standard deviation of our sample, so our S sub B, where the t is the critical value, and it's based on our degrees of freedom of n minus 2. Let's take a look at an example. So is cardiovascular fitness as measured by time to exhaustion from running on a treadmill related to an athlete's performance in a 20-kilometer ski race? So the following data on x equals the treadmill time to exhaustion in minutes, and we have y equals 20 kilometer ski time in minutes. And they were taken from the article Physiological Characteristics and Performance of Top U.S. Biathletes. And here we have our data set. Remember that x is our treadmill time to exhaustion in minutes, and y represents our 20-kilometer ski time in minutes. So we're going to sketch a scatter plot for this data. We're going to have our horizontal axis be our treadmill time, because that's our input, and we're going to have our ski time be our vertical. And here we've got, showing those, our scatter plot. Now this plot shows a linear pattern, and the vertical spread of points does not appear to be changing over the range of x values in the sample. Now, if we assume that the distribution of errors at any given x value is approximately normal, then the simple linear regression model seems appropriate. So here we have our data. It reminds us what x and y are, and our scatter plot. So we're going to find a 95% confidence interval for the slope of the true regression line. So here we have our negative 2.3335 plus or minus 2.26 times 0.591, which is going to give us a negative 3.671 to a negative 0.999. So we're saying that we're 95% confident that the true average decrease in ski time associated with a 1-minute increase in treadmill exhaustion time is between 1 minute and 3.7 minutes. So our regression equation is 88.8 minus 2.3 times the treadmill time. And so here we're getting this from a bipartial mini-tab output. So notice we have all of our values here. We have our predictor, our constant, our treadmill, our coefficient, our standard deviation, our t, our p, our s, our residual squared, and our residual squared adjusted. We have analysis of our variances. So we have all of these pieces here. So this is our equation of the estimated regression line. This is the estimated y-intercept at A. This is the estimated slope B. This is our estimated standard deviation of B. And this is our S sub E. So this value right here is 100 times our r squared. It's what gives us that percent, right? The r squared adjusted is not used in simple linear regression, so we can kind of ignore that value. This value right here is our SS residual, and this value right here is our SS total. This value here is our S sub e squared, and this value right here is our degrees of freedom, so we have our n minus 2 there. So let's talk a little bit more about our hypothesis test concerning our beta. So our null hypothesis would be that B equals the hypothesized value, beta equals the hypothesized value. So often the hypothesized value is 0, and this is called the model utility test for simple linear regression. Now our test statistic would be T equals B minus the hypothesized value divided by S sub B. And the test is based on degrees of freedom of n minus 2. Now our alternative hypothesis is going to be that our beta is greater than the hypothesized value. When that happens, we're saying that the p-value is going to be the area to the right of t under the appropriate t-curve. If our alternative hypothesis, though, is beta is less than the hypothesized value, then our p-value would be the area to the left of t under the appropriate t-curve. And finally, if our alternative hypothesis was that beta didn't equal the hypothesized value, then we'd take 2 times the area to the right of t if we had a positive t, or we would take 2 times the area to the left of t if we had a negative t. So what assumptions do we need to make? Well, for this test to be appropriate, the 4 basic assumptions of the simple regression model must be met. So that first one is that the distribution of E at any particular x value has a mean of 0. So our mu sub E must equal 0. Second, that the standard deviation of E is sigma, which does not depend on x. Third, that the distribution of E at any particular x value is normal. And then fourth and finally is that the random deviation, so E sub 1, E sub 2, all the way to E sub n, associated with different observations are independent of one another. So suppose that the least squares line is horizontal. So would height be useful for predicting weight? Well, what is the slope of the horizontal line? Yeah, it's 0. So a slope of 0 means that there is no linear relationship between x and y. Now the model utility test, so let's say our null hypothesis is that beta sub 1 equals 0, versus our alternative hypothesis test that beta sub 1 is not 0. So this model utility test, it tests whether the slope of the regression line is a non-zero. So why is it special? Well, if y really depends on x, then x should be a term in the final model. So if beta sub 1 equals 0, then that is equivalent to saying that x is not in the model. So the variation in y is random and not dependent on x. Now the hypothesis test for our null hypothesis of beta sub 1 equals 0 and our alternative hypothesis test of beta sub 1 is not a 0. So therefore it tests whether the model is useful. Now if we reject the null hypothesis for this test, then we conclude that our beta sub 1 equals 0. And so x should be in the model, and the model is useful. So our test statistic is that t equals b divided by our s sub b. Let's go back to our biathletes problem. Remember the treadmill to exhaustion time, and then our ski time for the 20-kilometer ski run. So here's our data set, and we have our scatter plot. Now, even though the scatter plots indicate a linear relationship between ski time and the treadmill time, we're going to perform the model utility test here. So we're going to say that our null hypothesis is that beta equals 0, and that our alternative hypothesis is that beta is not 0. where beta is the slope of the population regression line between treadmill time and ski time. So we'll plug that in, giving us a t-value of negative 3.95, which yields us, because we have a degrees of freedom of 9, it yields us a p-value of 0.003. So using an alpha of 0.05, we see that our p-value is less than our alpha. And since the p-value is less than alpha, we reject our null hypothesis. So there is sufficient evidence of a linear relationship between treadmill time and ski time. Let's go back to our partial Minitab output from earlier. So here, if I take that negative 2.335 and divide it by 0.5911, or 5911, that's going to give me my negative 3.95. So this negative 3.95 in our output, this is our t-test statistic. And if you look just to the right of that, we have 0.003. That is our p-value. So statistical software usually performs the model utility test with our null hypothesis of beta equals 0 versus our alternative hypothesis of beta does not equal 0. And so being able to read statistical software outputs can be very valuable and very helpful.